Okay, students, good morning. Mm, Yeah, so what we saw in the last class was, I started talking about how we can make a, uh polycrystalline ceramic material. I took the example of MgAl2O4. So I said, let's say you want to make a thin film of MgAl2O4, and in order to make a thin film of MgAl2O4 using the sputtering technique, first requirement is to get the material, that is MgAl2O4, in polycrystalline form, which we call it the target material, and that target material can be used to uh, you know uh, in the sputter unit, and then you subject it to the process of sputtering, and then you get the thin film growth. So that process we'll see later, but what I started uh, telling you was the importance of uh, getting the initial starting material. So that's why I took the example of MgAl2O4. I said the starting materials are the constituent materials of the cations, magnesium and aluminum. Magnesium. So you start with magnesium oxide and aluminum oxide, Al2O3, which are the most stable oxide forms of magnesium and aluminum. And then you start getting the reaction to happen. And I said, if you take two blocks of magnesium oxide and aluminum oxide, and as you can see in the picture, if a reaction has to happen, so that's where the interface is the place where the nucleation is happening, because that's where the migration of magnesium and aluminum ions happen. And I also mentioned that in a solid state process, the diffusion lengths of these ions are very, very small, all the way from a few nanometers to micrometers. Diffusion also can be uh, enhanced. Diffusion lengths can be enhanced by heating the compound at higher temperature. But the limitation of the highest temperature you can go to is, of course, the melting point of the material. Okay, so that's a product area or volume at which point the new phase forms. Okay, I said temperature plays a very crucial role. So what we see is that this is what it is. So if these two colored blocks are, one is say magnesium oxide, the other one is aluminum oxide, that's the interface where you'll start seeing the formation of the new phase. But the problem is the process is absolutely slow. So how do I improve the nucleation process so that the compound formation becomes faster? So I remember in the last class, I also mentioned, if I start from a large polycrystalline target of magnesium aluminum oxide, which I use in the thin film growth process, I will be able to grow a thin film out of it within, say, 20 to 30 minutes. Of course, this depends on the thickness of the thin film you need. Typically, crystalline films are obtained up to 400 to 500 nanometers. So all the way, you can get a thin film of a single monolayer, 10 monolayers, 200 nanometers to 400 to 500 nanometers, crystalline thin film. But the same bulk counterpart of MgAl2O4 to make the polycrystalline bulk material through this process that we are looking at takes several days. So after which, when I have the polycrystalline material, using it in the thin film growth process, you will get the thin film of the same material in a crystalline form within few minutes. If you just want to get a single monolayer of the same material in a crystalline form. Why that is? Because in a thin film growth process, remember I also mentioned in the beginning that if it is a thermal evaporation, the source is melted and vaporized, and the vapor is collected on the substrate. And in the process of sputtering, you break the target, the polycrystalline target, into individual atoms. How the breaking is done, we'll see. But so it's basically an atomic process. Thin film growth process is an atomic process. You provide a large number of nucleation sites, which you can understand from here itself. Look, in this particular case, yeah. So now imagine, let me take, so if I break this one and this one also into, let's say, I'm just trying to pick a pen here, color, different color. Okay, let me put it this way. Yeah. So let's say I break this up into smaller particles, right? I can do it. It's just a mechanical process by which you try to plunder this uh, blue colored block, and I do the same thing with the red colored block also. So I get, of course, particles of different sizes, and for a given volume, when you start plundering it down, this is a typical top-down approach we talk about when you're making nanoparticles. This is one way of getting the particle size reduced of any given system, and this mechanical attrition leads to uh, attaining lower particle sizes, all the way down to microns, even in some cases to nanometers. To go to nanometer size, you need to do this attrition, mechanical attrition, for a long period of time. But if you take any ceramic body, like a small piece of ceramic, and if you subject it to even a normal uh, hand grinding by applying the force with the hand using a mortar and a pestle, um, after using the normal hand force for about half an hour or 45 minutes to 1 hour, what you typically get is these particle sizes of a few microns. Microns in the sense anywhere from 25 to 200 microns. 200 micron particles are coarse, and 25 microns particle sizes are, you feel these particles become soft in the hand. So nanometer particle sizes require special equipment to do that process of attrition. It takes a longer period of time. You keep them in mechanized ball mills, and then these ball mills do their job of breaking up the particles further with the aid of solid ceramic objects, which which are used to crush these particles over a period of time. It could be 24 hours, 48 hours, or 72 hours. But for the normal process of solid state reaction method that we are looking at, typically the particles, when you reduce the size of these two blocks, the particle sizes will be of the order of a few tens of microns. So now I take a mixture of these two, which means I have So when I nicely mix this up, what I get is, I'm seeing, so this is all with physical mixture or mechanical mixture, anything is possible, right? See what you see here is already, so first step is we reduce the particle sizes by, mechanically attritioning these two solid bodies, because in this particular case, the nucleation happens only there. So for the nucleation to extend on both sides to convert those two colored blocks into the final compound, it takes a lot of time. So in order to increase the nucleation process, what I've done is I have reduced the particle size by mechanical attrition of both the blocks. Now, by mixing, I get this scenario. Okay. Now, if I take this powder mix and then heat it up, there are several heating steps involved. Normally, I also mentioned that for a polycrystalline system, if you do 0.92 of, you should not exceed something like 0.92 of the melting point, right? That is actually good enough to basically give you a polycrystalline material. So these heating steps of these powders would be 1, 2, 3 times you have to heat in order to ensure homogeneous mixing leading to the phase formation. That means if the melting point of, so suppose you want to fix the melting point at 1000 degrees centigrade, depending on the lowest melting point of one of these reacting compounds. So the first heating could be not directly to 920 degrees Celsius. It could be at 875, 900, 920. In those steps you can go. At least 3 heatings are required. That means you break these powders, mix them up. First heating, again you take the powder. Some phase formation will be there, but still you may not ensure that both the compounds, all these particles would have reacted into the final product. So you do the second heating and third heating, and after the third heating, you probably have the final phase ready. Okay, so this is called the typical solid state reaction process. Of course, at each stage of this 1, 2, 3, one can do X-ray diffraction and see if the phase formation is there or not. It's possible. At each stage we can do. But the process goes like this. Yeah. Just to give you the sequence. So you start with these powders. Okay. What you see here. And the powders are taken inside a crucible. So you mix them up and put them inside a crucible. And this crucible itself is a ceramic material. Typically, these crucibles are made of aluminum oxide or zirconium oxide. These are high melting point compounds. Okay. So you can easily heat any material, any mixture that is kept inside close to 1700 degrees of centigrade or so. But the problem is if you go close to the melting point of the crucible material itself, there could be interdiffusion of species from the crucible into these compounds or the final compound. That danger is always there. So crucible-induced contamination is one of the main issues in solid-state reaction methods. This one has to really take care of. But of course, if a serious problem of ions diffusing from the crucible into the compound, say, happens at 1800 degrees centigrade or above, up to 1700 degrees centigrade, there shouldn't be any problem of diffusion. So typically, as I told you, alumina is used, zirconia. These are made into these shapes. They're then sintered. They're subjected to high temperature heating because you need a highly dense form of the crucible material. That itself is a ceramic process. Okay, so imagine the powder here is compacted and shaped in this form of a crucible. Okay. So the crucible with the mixture is kept inside the furnace. This is again the second crucial step, and you need to choose the right kind of the furnace depending on the temperature that you want to heat the mixture to. If 1000 degrees is required, you need a furnace with a certain type of heating elements. If you need temperatures up to 1500, you need a separate set of heating elements. 1500 and above, you have furnaces with different set of heating elements. This is always a challenge. And what is the maximum temperature that you can go with a furnace like this? I'll come to that. So this is how a typical furnace looks like. This is called a box furnace. These are all the controls. And you see it's already red hot there. So you can basically cook the material inside the furnace, right? Okay. Now, after heating these powders for several hours and doing it, few times, I said typically if these powders have to convert into a final product, the same process of mixing, heating has to be done at least 3 times for better homogeneity. Okay, now you get the powder, and at each stage, X-ray diffraction can be done to see how the phase is evolving, right? And of course, so the powder itself, if I want to do some electrical characterization of this powder, I cannot use it in the powder form because I need a solid block in order to give contacts on top of this material and pass current and measure the voltage drop. So there are some non-contact measurements. What are the non-contact measurements? Non-contact measurements are typically, non-contact measurements are spectroscopy measurements. Spectroscopy measurements do not require the material to be in bulk form, solid form. So I can take the powder and do a spectroscopy measurement. If this one is this material is magnetic, then magnetic materials do not require any contacts. No, I can take a few grams of the powder, put it in a capsule, and do a magnetic measurement. But if I want to do electrical characterization, I need to get it in a solid form. And if I want to use a technique, thin film technique like sputtering, I need the powder compressed into a highly dense solid form. So what is to be done is you take this powder, so this is a typical die and plunger. So you see this is a die and 2 parts of the plunger. So this one, the bottom one, small one goes at the bottom of this groove, right? And then once it is in place, you fill this volume with this powder. We can calculate if you want to get a tiny cylindrical slab of course, what you get is a diameter corresponding to this die, and the thickness can be controlled, and you can calculate the amount that is required to get a given thickness. So you fill this volume with that much amount of this powder, and this is a plunger that comes on the top. You can see it goes in the reverse way. Now this part goes inside, and that's where on the top you apply high pressure using hydraulic press. That's hydraulic press. So this whole assembly goes there, and then you apply a hydraulic press. So for getting small targets like this, small pellets for electrical measurements, even we can apply pressure with hand, a few pascals, and that is sufficient to pack these powders into compacts. So after compacting using this hydraulic press, when you take the top and bottom plunges out, what you get is see, it comes in this form, right? Of course, these are small pellets. I call them pellets. I can use them for electrical property measurement or a dielectric measurement or a ferroelectric measurements if these are ferroelectric materials. But compact is a must. But just by putting this powder, compacting it, doesn't ensure high densification of these compacts. See, we have physically brought the particles together, right, from this powder form. By applying a high pressure, we are able to compress this powder into a smaller volume. So that means the particles have come together, but then the particles have not coagulated. There is no reaction between individual particles to form a solid that gives you high density. If you measure the density of this, it will be almost like your chalk piece. You know, chalk piece. If I take that long chalk piece, I can easily break it because it doesn't have high density. Because chalk piece also is made like that. I take a white chalk powder, put it in a mold like this, get it in that long cylindrical form, right? And then you subject it to very small amount of heating. Because I just want the particles to come together, but not give me a density which is 95% of its theoretical density. Because the whole idea of using a chalk is with a little bit of pressure, I want the chalk particles to come onto the board. But at the same time, I want a solid piece. But so a chalk piece that looks smoother on the surface, if you actually put it under a microscope, it starts showing all kinds of grains, grain boundaries, and lots of voids. Because I didn't bother about making it a highly a dense piece. Then I just can't write on the board with the normal force, right? Same is the case here. These are highly porous pellets, which is again not good for any electrical property measurement because you can do electrical property measurement only when you ensure that these pellets have a high degree of density. And how do you get that high degree of density? You need to make these particles to coalesce with each other. Right? That's called the process of coalescence. For that, I need to again heat these particles or pellets back in a furnace. That process is called sintering process. So the initial process of heating all these individual powders to get the final compound is called calcination, right? You put the powders there, heat it up, get the powder several times. You grind it up again, back in this crucible, heat it, and when you're sure that the final composition has formed in this powder form, after confirming it with X-ray diffraction, then the next step is if you want to go for physical property measurements, you need to make these solid bodies. One is in the form of a pellet. I can also make it in the form of rectangular bars, which are good for electrical property measurement. Okay, now you see that. The process is, now we have all kinds of hydraulic pressures, high temperature, automated pressure systems available to get not only small pellets for electrical property studies, you can get targets of these sizes. So, the one you see here, typical a 3-inch target is what is 4-inch target. These are all required for sputtering. So that means, you see, what you're seeing here is the powder compositions, initial ones that are transformed into the final compound, I made a compact of those for physical property measurements. And I can also get them in bigger disc forms, which are required for thin film growth. So that means the polycrystalline form is obtained in this highly dense target form, and I remove the atoms again using the thin film growth process and deposit them in the form of a crystalline thin film. That's a process we'll see later. But this is all very crucial, because if the material doesn't form in its purest form, you can't go any further. So until, look, what I mean is, if you're starting compounds at 3, in the case of magnesium aluminum oxide, there are 2 compounds, magnesium oxide and aluminum oxide. I also gave the beautiful example of yttrium barium copper oxide, the superconductor, where you have 3 cations. So your starting compounds will be something like yttrium oxide, barium carbonate, and copper oxide. All 3 are mixed, and you get the final product. And if the final product has some impurities, then you always have to deal with those impurities. That means the heating is not sufficient. You go back, subject the powder to the heating process. You do that until the time that you get a completely single crystalline phase. That means single crystalline phase means X-ray wise, diffraction pattern shows you that there are no secondary phases present. See, when you're making the final composition of yttrium barium copper oxide, the secondary phases could be unreacted phases of the individual compounds. To start with, that's it. So you go back and do one more heating, and sort of that'll take care of the, the purity of the final compound. Then you get it in this form and sinterate. That means you again have to, so basically you have this process, heating, this one, and of course this goes several times, and the powder is pelletized, right? And these pellets are sintered again. You need to sinter them, and these are the sintered compositions. Okay, so you see how many processes are involved for you to first make a polycrystalline material in the best possible form, and also to get them in a form that can be used for doing physical property measurements, and also use them for thin film growth. Okay. Okay. Now, yes. So these being polycrystalline systems, again, I go back and show the same microstructure. So in spite of the fact that you subject the powders to high temperatures, because you're not melting them, it's not required to make a polycrystalline material. Even though you go to 92, 93% of the melting point. So now you may understand that the 92% of the melting is actually required to coalesce these particles. And what we have done in this process also is that, all these individual particles, now you see here, so a large number of nucleation sites have been created. Is it not? You can see that. Now, see, I have created a nucleation site there, nucleation site there, nucleation site there, nucleation site there, and so on. So all these nucleation sites grow, and so the nucleation here leads to crystalline formation. Nucleation there also leads to crystalline formation. But since you're not giving so much of time like the way we give to the molten compound in the case of single crystals, because there the cooling process is very long. And if the cooling process of the same compound to get a single crystal is, say, 1 full day, Here, the cooling process is just a few hours. But there, you in the single crystalline form, you start from a melt. Here is just from the powder. So this is the reason why the nucleation that starts extend to a certain extent, and it stops at this boundary where the nucleation from the neighboring boundary also stops. So you have a two energies here. So gamma G, the formation energy of the grain, gamma GB, the formation energy of the grain boundary. Okay. So if the formation energy of the grain boundary is equal to or greater than the formation energy of grain, so granularity certainly settles down. And this is a key in the case of polycrystalline systems. So you cannot do away with these grain boundaries unless you increase the temperature to close to its melting point, and also follow a slow cooling process, at which time even you give enough time for the atoms at the grain boundaries also to form into regular lattice positions, and then there'll be a continuity of the unit cell growth across the grain boundaries. Otherwise, a typical polycrystalline system will always have these grains and grain boundaries. Yeah, you see this. It's grain boundaries. This is a case. This is a case probably when the when the polycrystalline block is heated to lower temperatures. You still have these voids. See, but if you go to the next higher temperature, much lower temperature, you see more voids and smaller grain boundaries. And so this is the lower temperature T1, T2, and T3 here. This is the best you can get for a given sample. And probably for this system, you can't go to a sintering temperature more than what was used here. Beautiful example of a textbook example of a polycrystalline material. So if this material takes, this is LCMO, lanthanum calcium manganese oxide, another very interesting system that shows magnetic properties, and also it's useful in making thin film based TMR devices, tunnel magnetoresistance devices. Okay, but I also mentioned that today the physics of controlling the grain boundaries has many advantages. We'll see that. So I can grow this grain as one layer, this grain as another layer, and then you have, we create an artificial grain boundary. So that's possible with the so-called multi-layer growth. So control grain boundaries. I can't do anything with the polycrystalline bulk material like this, but then I can get a controlled grain growth using the thin film growth process. Then we can do some real wonders in terms of looking at the physics of the electrical transport process via this barrier, and also in terms of envisaging very useful devices. Yeah, that's what it is. See, I can create these artificial layers with the specific thickness of those barriers. That's what I mean by controlling those grain boundaries. And many of the devices use this controlled way of getting those multi layers with a specific amount of thickness of these alternating layers. Typical example is tunnel junctions. Okay, so I have the crystal. I have the silicon crystal. This is you can see that 8-inch silicon wafer. which is supposed to be crystalline. So you grow the crystal first of all by Czochralski method. I also mentioned that silicon can be obtained in a monocrystalline form, single crystalline form, or a polycrystalline form. And a photovoltaic solar panel made out of a polycrystalline silicon has lesser efficiency, less expensive also to get those photovoltaics. But if you want to have a single crystalline silicon photovoltaic, it's much more expensive because you need crystals like this. And the crystal growth process itself is very complicated. So you can grow these large crystals and then you cut them, slice them into these thin wafers, and these wafers then are packaged and device fabrication is done. And for device quality wafers, you expect such smooth morphology. And just again to complete that, it's all the way from just simple silicon dioxide sand to solar panels. You get silicon ingots there and purify them, and then dope them and make them P-type, N-type silicon, and fabricate the solar panels. Yeah. So now, the one very important aspect is in thin film growth, material processing, temperature plays a very crucial role. You just can't have a universal furnace to make all kinds of materials. You have sulfides, oxides, carbides. Some need very high temperatures, and some of the even to make an alloy, you need extremely high temperatures. Where do you get? How do you get these high temperatures? You know, and even in thin film growth, sometimes the substrate has to be heated to 400 in some cases. In some cases, you need all the way up to 800 to 1000 degrees centigrade during the growth process. Okay. So a typical furnace looks like that. This, again, I told you it's called a box furnace. And when you open it, that's what you see. And these are the heating elements, elements or coils or rods. Okay. And you keep your compound inside this volume. Yeah. And then once you close the front door and turn it on, the furnace starts producing thermal energy. It'll get heated up, and then you cook the samples. You know, the initial heating process, heating after compacting them. So typically, the interior of a furnace looks like that. Once it is red hot, that means you're already above 800 degrees centigrade. See, you have heating rods on the sides, this side, that side, and the back side also. And sometimes there are heating rods on the inside of this opening itself, so that you have uniform heating coming from all sides, top and bottom too. Top also, not the bottom side. So this bottom platform is meant for keeping those samples. That's what it looks like. You also have what are called, this is a box furnace, this is a tubular furnace, right? So in tubular furnaces are required if you want to heat any given material at a certain temperature, and also with a gas flow. So see, when you're heating this particular compound at say 900 degrees centigrade, this heating is at ambient. You're doing it in air. There are some compounds that require heating in vacuum. That means the furnace has to be evacuated down to 10 raised to minus 6. If you have alloy compositions that you want to heat, in order to, without heating, there is no crystallization. So I make an alloy and I need to heat this alloy at 900 degrees centigrade, say for 12 hours. And I can't put this alloy composition inside a furnace like this and start heating it up at ambient. No, why? Because the alloy can get oxidized by reacting with the with oxygen in the air. So I need a vacuum furnace. That means this whole volume has to be evacuated, and vacuum furnaces are very expensive. It's difficult to afford and maintain vacuum furnaces, because imagine at 900 degrees centigrade, I need to maintain, in order for an alloy not to get oxidized, at least 10 raised to minus 6 torr is required. So it's continuous pumping. Okay. So to avoid that process, imagine now I have a tubular furnace. So I have the heating elements inside, where the same material is kept inside this tube, and then I can create a vacuum inside this tube, easy, or I start passing inert gas through the tube. It's as good as heating the compounds with no traces of oxygen. It's a much better way of heating compounds that require no traces of oxygen, right? It's easy. I can just connect it to a vacuum pump. After all, in that case, I just have to evacuate only the tube volume, or I just connected to initially after loading the samples, I connect one end of the tube to an argon cylinder, inert gas, and during the heating process, the argon is continuously flowing through it, and it makes sure that there are no traces of oxygen inside. It's a very nice way of heating up compounds in an oxygen-free environment. Yeah, that's what it looks like. So you have a coil again like this, and your quartz tube. This is a quartz tube. Quartz tubes are good if up to about 800 degrees centigrade. But if you want to heat the compounds beyond 800 degrees centigrade, then you have to go for a ceramic tube. This has to be replaced with these large ceramic tubes, because quartz cannot withstand temperatures above 1000 degrees centigrade. So this can be easily replaced with a long ceramic tube. Yeah, you see that. So today the way heaters are made, well, these can be made at in the lab. You can just you take a wire. I can take a copper wire, wind it up. I can a coil of copper I can use for creating a magnetic field, and also any metal made in the form of a wire. When you pass a current through it, um, because of the resistance, you can also calculate the resistance that is required to heat up the coil to attain certain temperature. Resistance heating is the most common way of producing high temperature, right? You see that? That's how, yeah. You see? These coils, when you pass a current through these coils, set of coils. So there are, inside these furnaces, you have a large number of sets of coils. So on the top, probably three on the sides, and three on the closing door. So you can imagine, and you're passing a current of anywhere from 20 to 40 to 60 amperes, depending on the size of uh, the furnace. And you see that these are all again high temperature ceramic blocks that can withstand temperatures more than what these coils can produce. That's important, and so you see that you need a long wire, several of them, and when current is passed through this, and this forms the interior of a furnace, and you see that the whole volume of the furnace getting heated up in a uniform way. You can also have long coils like this. But what is basically used for making these coils? One of the most common materials, one of the most common heating elements is what is called nichrome. nichrome. Nichrome is an alloy of nickel and chromium. It is 80% of nickel and 20% of chromium. Yeah? Well, these alloys are chosen for various reasons, because when you make a heating element using these alloys, see, the heating element that you see here, which goes into making a furnace, it can also be used in making a heater for a thin film growth process. I told you substrates have to be heated, right? And you're using it for several years. So I put a crucible with some material inside. I turn it on, so current is passed, maximum temperature is attained. Then you cool it back to room temperature. Again, next day you start the furnace again. So furnace, these heating rods are subjected to continuous heating to higher temperatures and cooling. So they go through this thermal cycling several hundred times. So they should also be oxidation resistant because they're heated in air. Something like copper, if you heat it to very high temperatures, cool it back, again do it, right? Copper can get oxidized even at room temperature easily. If you take a shiny piece of copper metal, copper is also very expensive, tiny piece of copper metal, leave it outside, you see after a few days, its surface become, you see a coating on the surface. That coating is an oxide of copper. So these alloys are chosen because they give the right kind of resistance to be used as resistance heaters, and also they can withstand all the thermal cycling processes. Okay, that's important, and they should be at the same time they should have the properties of malleability and ductility. In some cases, a given element is very good for to be used as a heating element, but then it has a problem of getting drawn into wire form easily. So then the other element is added in order to improve that property. So nichrome is a very common material that is used if you have to get temperatures almost up to 1400 degrees centigrade. Okay, and along with nichrome, you have another very special material called canthal, again an alloy. Canthal. Canthal is an alloy of iron, chromium, and aluminum. Iron, chromium, and aluminum. Okay, so many of the furnaces for low temperature heating, all the way from 600 to 1500, canthal heating elements are used. Very common. And canthal and nichrome are also used extensively for making heaters during thin film growth. Of course, thin film growth doesn't require temperatures of this order. This is another great advantage. If the bulk counterpart requires 1000 degrees centigrade to be made into a polycrystalline bulk form, when I'm converting it into a thin film using one of these thin film process, where of course the heating of the substrate is required, I can get a crystalline form of that thin film, of that material, probably at 700 or 750 degrees centigrade. Because you know why? That while making the thin film from the bulk counterpart, I break up the bulk into its individual constituents. In fact, atomize it. So there's a difference between the particles of larger particles, 25, 50 micron particles reacting with each other. Yeah, like this. And yes, these are the particles I was talking about when we break this. When we break that solid into smaller particles, this particle size is still of the order of 25 to 50 microns. Is it not? Yeah. No, that's a reaction happening between two 25 micron particles or 50 micron particles. And the reactivity is much faster compared to what happens between two larger blocks of these two constituents. Obviously, I've created, instead of one nucleation site there, I created thousands of nucleation sites by plundering each of these blocks into smaller particles. Now imagine if these particles are further reduced down to nanoscale. That means I increase the nucleation sites by probably 1,000-fold, close to 1,000,000-fold probably. You can calculate that. The size is reduced from, say, 50 microns down to 50 nanometers. You can imagine how many more small particles you can create. And that means those many more number of nucleation sites. And you go further down, I'm breaking it into individual atoms, right? That's what happens in a thin film growth process. Now, so I make the reaction to happen between individual atoms or small, very small clusters, nanoclusters. Now you can imagine the reaction kinetics that happen in the case of a thin film, where atomic particles start reacting to micron-sized particles in a solid-state process, to reaction between these two blocks, right? So the fastest reaction here in the case of a thin film growth process, and the slowest here. So there's a direct correlation, because that's why I started with this example. So this is breaking up these into small particles of 25, 50 micron size particles, and to enhance the reactivity, because I created more number of nucleation sites by breaking them up. And in the thin film growth process, I still go to much lower particle sizes, or I even atomize them. So I have all the atoms of the constituent compounds in the perfect stoichiometric ratio, and the reaction can happen much faster at a much lower temperature. That's why I said the ceramic body, polycrystalline a body that requires say 5 to 7 days of preparation, several rounds of heating for the compound to form, I can transform it into a crystalline thin film within a few tens of minutes. This is the beauty of thin film growth. The reaction kinetics are much faster there, and you're providing a proper platform to for the unit cells to form, and you're also providing thermal energy. So that thermal energy need not be as high as what you require for this reaction for its bulk counterpart. Okay. Okay. Good. I'll stop there. You have any questions? We shall meet tomorrow, of course, at